So let's have a look at an example where we'll implement this code and see how the Arduino board reacts accordingly. So what I'm going to try and do in this example is to make it that whenever we push the push button, the light will go on, and whenever the push button is released, the light will go off. So again, I've got my basic code over here as what we've seen in the past. So the first thing I'm going to do is I'm going to indicate what my input and output pins are. Okay, so I'm going to have pin 7 as an output, and then I'm going to have pin 4 as an input. Okay, so these numbers can change depending on which pins you're connecting your input and output points, but for the specific configuration that I've got in that box that I've shown you earlier, we're going to have to use pin 4 as an input and pin 7 as an output. Okay, I'm also going to declare integer var r over here to be equal to 0, because I'm going to be using the input as a variable resistance, as we'll see soon. Okay, I've got a while loop, which will be while 1. Okay. And now, basically, I've got to check if a certain input pin is high, then obviously the output to the LED needs to be high. Okay, so for that I need the if statement. So if the digital read of pin 4 is equal to a high, then I must make it the output, which will be a digital write of pin 7 to be high. Okay, so this is a straightforward if statement, looking if the input is high on a certain pin, the output would be high. But we need to take into account what happens when you release the button. Obviously then it won't be high. So we need to make sure that there's a certain condition, so that if this is not high, it's not going to stay high, it needs to actually go down to low. So therefore I'm going to have an else statement where I'm going to say digital write of 7, low. Okay, obviously write is misspelled there we go, write 7, low. As you would have also seen in the videos when I go into programming with CH, I do explain in terms of why even for the else statement over here it's better to have brackets to open and close, even though it's only a single statement over there. Okay, so essentially that is the one part we're going to do. The other part I'm going to be having in this piece of code is I'm going to read what is the analog value on the pin of A0, and then I'm going to write that to the output on specifically on pin 10, which is an LED. Okay, so var is equal to analog read of A0, and then I'm going to analog write to pin 10, var. Okay, let's run this and see what happens. Just something that's worthwhile mentioning over here is always keep in mind that Arduino program that we had to start off for the communication between your computer and Arduino board, you might have to sometimes disconnect that and connect it again to get things working, and then you might sometimes find you might have to actually close that program completely, restart it from scratch, and then try connection again. It does happen that there's sometimes connections don't happen automatically and that you need to restart things to get things activated. Okay, so let's have a look at how it reacts on the Arduino board. So let's have a look. We've got our circuit going. You can see lights flashing over there. That's indicating that there's communication happening between the computer and Arduino board. When I push the push button, the red light goes on. And when I release the push button, the red light goes off. So that is what we expected would happen. Let's have a look at the pot or the variable resistor. What happens when I start increasing it? As I increase it, you'll see that that green light over there is starting to get brighter. Eventually it gets quite bright. Let's go and get more brighter and more brighter. So that seems to be working, which is a good thing. And then it switches off as I keep on turning. Now it's dim again. So as I keep on turning this, it gets brighter and brighter. And as we continue turning it, it goes dim again. Okay, let's continue with still turning this knob. So it gets brighter and brighter as I'm turning and increasing it. Now I'm turning it slowly because I want you to sort of see what happens and how it is affected. And then it goes down again. And so I keep on increasing it, gets brighter as well. And eventually it gets to the point where it is fully turned and the light is on its brightest. Okay, so this light has increased in terms of getting lighter and lighter or brighter and brighter, and reset down to 0. So there's 4 cycles as we turn the knob. Right, so after we've done the demonstration, we can click on stop and it will stop the program. It will indicate over here that there's the exit code 1 because it was a forceful stop. Process failed to respond, forcing abrupt termination. It's just that we stopped the program in this specific CH program, and it wasn't because there was this while loop of continuing infinity times. One of the things that we did notice is that this output carried on with the brightness of the LED. Went through a cycle, and the cycle happened 4 times, where it would keep on increasing, get to the maximum point, and then go back to 0. Okay, so why did this happen? Well, something we need to keep in mind is that this analog input that we're reading over here is a 10-bit analog input. Okay, so that implies that we've got 2 to the power of 10, which is equal to 1023. Well, 1024 minus 1, which is 1023, which is the smallest, the largest number. Okay. When it comes to writing the PWM values, we're working with the 8-bit number. Okay, so 8-bit number, which implies we've got 2 to the power of 8, which is equal to 256. Okay, now if you look at that, 256 goes into 1024 times 4 times, right? And so we're able to see over here that's the reason why the cycle is happening. It gets to 256 or 255. As soon as it gets to 256, it drops down. It's an overflow that happens, and we see it going back to 0, and then it starts increasing again up to the next cycle where it gets up to 256, goes down again, and gets seen as being 0 again. So this overflow does happen. So one way to overcome that is to actually divide this by 4. And because we can sort of see that it goes in 4 times over there, and we're able to then see how that would respond if that would work correctly. Okay, let's run it and see how it works. So now again, let's just push button, see if that works. Every time I push it, the red LED switches on. So that, and then switches off as soon as I release it. So that seems to be working. I've turned down this variable resistor completely. It's time to increase it slowly. You'll see the LED does start increasing in brightness. Keeps on going, and as I'm turning this, it just gets brighter and brighter. And I'm turning it all the way right up to the end, and it hasn't gone dim again. So that divide by 4 that we've added into that line seems to solve this problem to allow for up to 256 for the PWM output. I'm going to use the same piece of code, but I'm going to modify it a little bit. So essentially what I want to do now is I'm going to actually remove this analog write and read commands, because for this section we don't need it. We've looked at how the correlation between the input being a 10-bit and the output being an 8-bit number works, so we'll leave that for now. Now I'm going to be making a few changes over here in terms of this digital read and write commands. And for what I'm going to do is for this piece of code, every time I push the button, the push button, I want it to either activate the LED, and if the LED was activated, it would deactivate it. So it will toggle the output of the LED every time I push the button. Okay, so for this I'm going to have another variable that I'm going to create over here. It's going to be IOF. So this is IOF is going to stand for input output flag. So essentially I'm just going to use that and toggle this between 0 and 1 and alternate it depending on every time that the digital read is equal to high. Okay, so if this digital digital read of pin 4 is equal to a high, we need to therefore first check if IOF is equal to 1 and then change it to 0, or if it's 0 then change it to 1. Okay, so for that I'm going to say if IOF is equal to 0, okay, then IOF needs to be equal to 1. So now we're toggling the value of IOF. So every time we see that the input on pin 4 is high, it's going to change from 0 to 1. Okay. Otherwise, IOF will probably be 1 if this condition is not true, and therefore IOF needs to change to 0. So we can have our statement over here of IOF is equal to 0. Sorry, I need to put that into curly brackets. IOF is equal to 0. Okay, this is our statement over here. I can take out as well. Okay, so basically we're going to be keep on checking this in this infinity loop. If pin 4 is equal to a high, we need to first check if IOF is 0. If IOF is 0, it's going to change it to 1. Otherwise, IOF must be equal to 1 and we'll change it to 0. Okay, so that's what that if statement over there is doing. Right, is there anything else we need to do over there? No, not really. So now what I need to do is I need to have an if statement over here that will take into account in terms of checking if IOF is equal to 1. If IOF is equal to 1, then it needs to output a high to that specific pin. Otherwise, if IOF is equal to 0, it must output a low. Okay, so if IOF is equal to 1, then the digital write on pin 7 must be equal to a high. Okay. Otherwise, if IOF is equal to 0, we need to have that digital write on pin 7 is a low. Okay. Now, so let's just quickly go through this code and see what we've done. So again, we've got our inputs and outputs declared, we've got our variables, we've got the IOF flag or input output flag which is equal to 0. If we see that pin 4 is a high, then we're going to first check if IOF is equal to 0. If it is, then IOF would be equal to 1. Otherwise, IOF would be equal to 0. So it will toggle the value of IOF. Then once we've done that, we need to now go and output a value correlating to that. So if IOF is equal to 1, we need to then say, okay, well, therefore output a high value. on pin 7. Otherwise, if IOF is equal to 0, we need to output to pin 7 a low value, and therefore switch off the LED. So we're going to see every time we push the push button, it needs to toggle the light on and off. Okay, so let's see what happens when we run this. So what I've done now is I've actually deactivated this pull down resistor and I've switched the switch across. So now what you'll see happening is every time I push this button, the red LED is flashing on and off. And the reason for that is that there's now some charge that is now connected to this input pin from this push button, and it's fluctuating. The microcontroller doesn't know if it's a 1 or a 0, and so because of this fluctuation, it doesn't know should it output a 1 or a 0. Eventually the charge builds up and it goes on. Now if I go and I push it again, we expect it to switch off immediately, yet you will notice that it's still flashing. It doesn't know, should it go on and off. It's the situation, there's some charge still on that specific pin, and it's now probably busy discharging eventually, and then once it's discharged, depending on now if it's on or off, it will then go into the final state. So let's see what this LED should be the final state that it would appear as. It does keep on flashing because it does see a high and a low every time it goes through this code with that while one loop. It goes through infinity amount of times, so it's flashing at that rate that it's going through that loop. Okay, it seems like it hasn't stopped in terms of the position that it wants, that we haven't. It's still on. Okay, so it's very difficult to see that happening. So now I've activated that pull down resistor. Now when I push a pull down resistor or activate a pull down resistor, if I push the button once, it switches off. If I push it again, it comes on again. Okay, now you'll notice that there's times that I push it and it will stay in the same state. And that could be because there is, if you look at the switch inside, there's two metal plates touching each other. So these two metal plates attach each other, but as we think it's only touching one, but as a matter of fact, it's almost like clapping against each other inside. And that's the reason it sometimes stays on the same state. So you've got to be very quick with that push to make sure that there is a very short time period that it's activated and that there's no clapping happening between those 2 points or those 2 contact points inside the push button. So if I push it again, there we see it still stays on. Okay, there we go. Push it again. Now it switches off. So you'll see that the switching from the one state to the other state, even though sometimes we have to push it quite often to get it to recognize the activation, it is a more steady output that we get, and we don't get that flashing happening with the LED. Okay, so there it goes on again, and there it goes off again. So I can actually change this to be able to compensate for that by having actually the maybe a different resistor value inside there. I could also have delays over there in the code, but you want to try and prevent from using delays. And the reason for that is that whenever you've got a delay function in your code, it stops everything on the code. So if you've got a delay function, you could be pushing this button again to, let's say, deactivate the system as an emergency stop, and it won't actually happen because of the fact that there's a delay and it stopped everything happening on this board. So you want to prevent using delays and rather use external interrupts and have the code keep on running and checking those external interrupts than having to have or have external circuitry like different resistor values to do that discharging of the button and having to have any delays in your actual code. Then we can stop the code over there. Alright, so as you saw, the code runs very quickly, goes through this while loop numerous times. It goes and toggles between 0 and 1. The pull down resistor was very much needed, as you would have seen that it did change the toggling of that light because of the input that wasn't, there was no indication to the program whether it was high or low. It was, you could have had it in terms of the contact points clapping against each other, which makes it on and off all the time, or it could be some capacitance on that pin, and that capacitance needs to discharge and before it actually allows for final state to happen. So that's the reason why that pull down resistor is very important. It discharges that capacitance on that pin and allows it to then be a more clear indication of the input that you're getting. And then depending on whether it was a 1 or a 0 that we changed and toggled this IOF variable, we were able to output with the digital write either as a high or a low, depending on the state of this IOF variable. So now we've looked at how we're able to look at the inputs and outputs, but let's get back to the beginning of our code that we looked at earlier that had actually the analog input and output. And what we want to specifically look at is how would you go and control a servo motor. Okay, so we had a look in the first video session in terms of how to declare a servo. So we had our different modes. We had servo.myservo, and then we declared myservo.attach to pin 11. Okay, so we've got on pin 11 the servo attached. Now we come into the while loop again, and so what we're going to be doing again, we're going to be changing the servo position depending on the input of the variable resistor that we're getting. So again, we're going to have VARR is equal to analog read on A0, and then we're going to have my servo dot write of VARR divided by 4. Again, we're dividing it by 4 because the output of the PWM to the servo is up to 255, while, or in other words, it's an 8-bit number compared to what we're reading on the analog to digital pin, which is a 10-bit number, which is up to 1024. Okay, so let's run this and see what happens with the servo as we turn at variable resistance. Okay, well, there is an error over here. Servo.myservo. Why is that? Oh, we shouldn't have the dot over there. Let's see if that runs now.
Alright, so this is the servo motor, and you'll see the little white arm over there that's turning. So depending on how I turn this variable resistor, it should show that arm moving. And you'll see as I get closer to the limits of it, it starts creating like a vibrating noise. Essentially because it doesn't know exactly what it's supposed to do. It's sort of at the end point and doesn't know if it should be going up a little bit more or come down a little bit. So it is vibrating a bit. So as we increase this, you'll see in more middle points, once there's the actual value of that variable resistor, the servo motor is not making any noises and is able to stay in a specific point. So you could go and assign a value, instead of having to have the VARR variable that you assign to the servo motor, you could assign it to a specific value of, let's say, 200, and it will go to a specific angle. So in this case, if you look at it, it's probably about maybe 270 degrees that the range is, maybe a little bit less, maybe about 250 degrees. So that's the range of this, full range of this specific servo. And so we're able to now control the actual position of it using the PWM. So it's again to do with how many degrees and the position of it, instead of actual how, well, in the previous case we had to look at the flashing of the LEDs. Keep in mind you do get servo motors that are full rotational, and these do allow you to, with the PWM output, it could give you a full rotation. You get some servo motors that might be only 90 degrees, some servo motors that might be only 180 degrees. The same principle in terms of output of the PWM as you would do with the LEDs can be actually used to control motors and the actual speeds. So that would be the command you would have for the green light. So we are able to, depending on the PWM output that we're giving, again ranging from 0 to 256, and again correlating with the voltage from 0 to 5 volt. Depending on the voltage that we are able to produce coming out of the PWM, we're able to then control the speed of the motor. Keep in mind that motors are not linear, so you're not going to have it as you start increasing the voltage to the motor, it has to overcome that magnetism and to get going. So sometimes you might have to have quite a bit of voltage to overcome that magnetism to start the motion of the motor to turn, and then only as you turn it slightly increasing the value of the variable resistor, then only would the motor start speeding up. So these are things to keep in mind for future projects, and so you can actually use a very similar code and techniques to control motors and therefore the wheels on a specific robot.
What that we did over here is we had server space my server. Please note that there's no dot in between over there, otherwise it might not work. But we've got my server dot attach to indicate that the server is attached to pin 11. And then basically what we did is we read from the A to D converter over there on pin A0, and we stored it into VARR, and then we outputted it to my server.write. And again we divide by 4 because of the 10-bit and 8-bit scenario between the input and output values. Keep in mind, you could have also done something of a very similar effect. I'm going to comment that out over there, of my server.write, and you could have like a variable of, let's say, 180, and that would then output a value, a PWM value of 180, sorry, not 280, and that would output a value of 180, and that would then correlate, the server will move to a specific position that will correlate between 0 and 5 volts for that specific server, again depending on how many degrees that server might be able to rotate.